Dear guests, dear colleagues, dear Professor Thomas Bolander. Welcome to this inaugural lecture. My name is Per Brun-Brockhoff. I'm head of department for DTU Compute. Now, becoming a full professor at DTU Compute is, at DTU in general, is a long process. As I usually say, apart from the 20, 30, 40 years of hard work by the candidate, also in our system it's kind of like a long and serious process to get to this point. So I'd like to just share a bit of brief recent history on this process with you. Now, more than 1 year ago, actually back in November 2018, we submitted what is called kind of an analysis of the situation to DTU Central with the intent for the section of algorithms, logics, and graphs to strengthen its position in artificial intelligence and the collaboration with math to sort of cover the increased understanding of the mathematical foundation of AI. That was part of it. It's a long analysis. I'm just going to share a few lines with you. And also, the strategy would focus on understanding basic aspects of logic and what it means for the understanding and analysis of artificial intelligence. And also that the engineering challenge in all this surely also is to take together successful AI methods with the logic-based analysis and understanding to actually better understand and explain what is going on. So, not surprisingly, with these and many other good words, the Dean of Research, Katrine Krogh Andersen, and the Academic Council approved that we were going to announce the position. We're just getting started. Then, in the announcement, similar words were, of course, expressed that the position should cover, and that's then important, research, research-based teaching, and research-based public outreach activities within logic and AI, not the least. And the successful applicant, which we now know who was, will have the responsibility to strengthen the research in symbolic AI at our department, as well as the integration of this with other AI approaches like more stats and statistics and database AI. And there is a long list of things that the successful candidate was supposed to be expected to come up with. For instance, and again, I'll just share one or two lines. To initiate and develop cross-disciplinary research, combining logic-based AI with other approaches of AI, and the mathematical foundation of it. And then also investigating ethical, philosophical, legal, and/or societal aspects of AI. That is also of importance. And engage in excellent research communication at all levels, including public outreach to general public, special audiences, and invited talks at international research conferences. So we had a deadline in mid-January, that's almost a year ago, and the evaluation committee sort of were quite agreed about that Thomas was well suited for the position. Of course, a very long and detailed evaluation on the excellent research, which is part of it, of course, that you have done and are expected to do in the future. But then a couple of things that I want to highlight here. Then also, of course, your ability to engage and make students happy when you teach. That was mentioned as a very strong feature of you, Thomas. You had the Teacher of the Year award back in 2006, and you have many other nominations since then. And then, of course, your very impressive and extensive, I quote here, record of outreach and dissemination activities in written press, TV, radio, science and cocktail type events, etc., 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 etc. The etc. part I said, it was not in the evaluation actually. And then that sort of also had the peak when you had the Hans Christian Ørsted medal, which was later compared to the evaluation here, but that was quite impressive also, Thomas. So not surprisingly, after we had the interview by the end of May, you quite soon after there had the letter from our president, Anders Bjarklev, that you were offered the position, and luckily for us, you accepted. And looking at your CV, to finalize, it's not a big surprise, of course, to every one of us that you were the one selected for the position. Your scientific area is, as I think probably all in the room know, artificial intelligence, social intelligence, logic, multi-agent systems, automated planning. Fits perfectly with the announcement. You are also, if we look at your CV, you're kind of a homegrown from a DTU perspective, right? You're from our own academy, grown to the Champions League team now. And this is great, of course, but you also had a lot of international collaborations and stays, so it's not that you haven't met the world, for sure. And I'm not going to list that. There's a long list of international contacts that you bring in. So let me just finish my introduction here by sort of noting that I find that you seem to be a perfect match with the announcement, with the strategy of our department. If I may quote, as it looks at the moment, we constantly improve those words. So in a few weeks, I'm sure they will be better. For now, some of the words say that we at DTU Compute, we really strive to advance mathematics and computer science together by exploring these synergies between science, technology, and all the surroundings around us, all the domains and the society where we are making a difference. This is our way to fulfill the Hans Christian Ørsted mission to make a difference in society, for the people in the society. And what we also have now is that we want to do this and want to be known for how we do our scientific and engineering contributions of all the novel methodology and technology that we provide for society, but based on a strong ethical, human, and sustainable mindset. And this was part of this position's announcement, and Thomas, I'm sure you will be a strong fighter for that at our department. So with this, I will give the word to you, Thomas, and I'm very happy to be able to. Thank you, Thomas.
Thanks. Thanks a lot. Thanks a lot for the beautiful introduction. All right. If it gets too loud, let me know, because I like to speak loud, and even if I have a mic, maybe I should take it away a bit. Okay, so thanks a lot for the beautiful introduction. So as you can see from the title on the slides, I'm going to talk about logic and AI for reasoning about others. So there will be a lot about the logic-based approach to AI, but as Pierre said, there's also something that I'm very interested in, combining it with machine learning and statistical approaches to machine learning. And I will also address that a bit at the end. So what does it mean to do logic? It's too loud. Yeah, okay. Thanks, Philip. Which one is it? Which is it, Mike? Which mic is it? Free? How about now? Too low? How about now? Okay. Right. And so what does it mean? It means social aspects of artificial intelligence. It means how can we make the future smartphones and robots and computers slightly socially intelligent, so it's not only us who have to try to understand how these machines think, but they can also start to understand at least a little bit of how we humans think. And since it's about artificial intelligence, AI, a good starting point might be to settle once and for all what AI is about. So what is it about? The father of AI, John McCarthy, tried in 1956 to define it. And he said, Artificial intelligence is the science and engineering of making intelligent machines, especially intelligent computer programs. So nobody's going to dispute that definition today. The problem is just that we don't really know what intelligence is. And as long as we don't have a good definition of intelligence, we cannot understand what artificial intelligence is. But if we look at what kind of properties we normally assign to intelligence, it's something like thinking abstractly, learning from experience, thinking logically, being able to plan. And these are all things we try to do in AI, making systems that have these properties and can do these things. And all of these things is something I'm going to address during my talk. Another way to think about AI is to say that, well, AI is when we make machines that do things that so far only humans have been able to do. And what could that be? Well, that could be, for instance, to deliver items in a hospital, take blood samples and medical equipment and bring that from A to B. And for instance, Herlev Hospital has been looking at this. So there was this news in 2017 where they say they want to be world champions of delivery robots. And well, that sounds reasonable. I mean, it shouldn't be too hard because you want to deliver items from A to B. Right? So you need to find a route from A to B, but we routinely do this with Google Maps and in our car GPS. It's a well-known and solved problem in AI. And then, of course, you also need to know where you are. But that is also a solved problem in AI. So this ought to be simple and easy, and you can easily make it work. But then, now, a couple of months ago, there was a new news about the hospital at Herlev Hospital. This is November 2019, and then it says the hospital are putting the robots in the garage. They were not able to work alongside humans. Okay, so we don't have these robots anymore. And the important thing, of course, here is that the robots were not able to get along with the human beings. Because the problem is not just bringing objects from A to B if there's also a patient and employees at the hospital. So then you somehow have to relate to that. And this is exactly the problem that these hospital robots had, that they weren't able to somehow get along with the human beings. And this is a very big and serious problem in AI. And if I think about the problems I solve in my work life during a day, there's very, very few tasks I solve that doesn't involve other people, that doesn't involve interacting with other people and trying to take the perspective of other people. So there's very little I can do of my work if I don't have these abilities. So when we have robots that don't have these abilities, that puts a really strict limitations to what kind of applications we can have for these types of robots and where we can employ them. So this kind of points to the fact that, well, trying to give these robots at least some level of social intelligence is crucial. They don't have to be, social geniuses in any way, but at least we want to have a future where we don't have to put these robots in the garage because they're simply too socially inappropriate to even be useful. So, actually, it's not an easy problem. And if you think about it, at first, they wanted to be world champions in delivery robots. So apparently they didn't think about the complications that could appear. But it is not that easy. What are the easy and difficult problems in AI? It's not clear from the outset. But actually the social intelligence, so being able to take the perspective of others, reason about others, trying to predict what others are up to, this is all social intelligence, and it's often mentioned as one of the free human cognitive abilities that are hardest to simulate on computers and robots. So we know it's a hard problem. But this also points to another fact, that maybe it's not so easy to figure out what is easy to do and what is hard to do in AI. Maybe it's not that easy to predict. And maybe it's not a simple thing where we can easily predict what is difficult in AI by looking at humans, right? So, of course, it could be that what is hard and easy for a human would be the same for AI, but it could also be completely opposite. And indeed, it's more opposite than it is alike. So, one way of trying to categorize or characterize the current level of AI is that well, it's still mostly specialized system we have that solves pretty well-defined and clearly delimited problems. So as a pretty robust rule of thumb, you can think that the more well-defined and clearly delimited a problem is, the easier it is to make AI that solves that problem. Okay, so this is also why already in 1997, it was possible for IBM to build the chess computer Deep Blue that became world chess champion. Then we can look at something like driverless cars. So getting along in traffic, well, there are still rules. So in chess, the point about chess, why it's so well-defined and clearly delimited, is that we have very few rules in chess, and there's a very simple goal you have to achieve. Well, if you're in traffic, there are also rules in traffic, and your goal is to get to your destination, but there are more rules, they're more complicated, there's a lot of more things going on there. So that's more complicated from the perspective of AI. If I then want a household robot that can help out a bit in my house, help cooking and cleaning and that kind of stuff, then from an AI perspective, that is even more complicated because it's even less clearly delimited and well-defined. But if we then look at it from a human perspective, then we would say that, okay, so we can have our kids help around in the house and help doing the cooking and the cleaning. They might not want to, but at least, I mean, in principle, they can do it. But they have to be grown up in order to drive a car. So that's more complicated for them, right? And for most of us, no matter how much time we spend on it, we will never become world chess champions, right? So the axis of difficulty is completely opposite between humans and machines. So for the machines, it gets more difficult the further we get to the right, and for the humans, it's the other way around. So it's hard to make a direct comparison. So that just makes also that AI is a difficult subject, and it's actually difficult to understand exactly. Okay, so but we could try to come up with a kind of general perspective on AI. So what is it that AI does? Well, in a sense, you can say it's about solving problems. Yeah, but any technology is about solving problems, right? So the problem that my dishwasher solves is the problem of producing clean plates. But that's not AI. So what is that difference between that and AI? Well, AI, it has to do with generality. It has to do with building systems that are not made to just solve one problem under one particular circumstance, but is able to solve a wide range of problems under a wide range of circumstances. Well, actually, but that is part of the difficult thing, right? But this is where we are pushing, and this is where we want to go. Okay, so one example could be that my household robot from before, and I would like to just give tasks to the household robot, tell it what I need to have achieved, and then it solves the problem. So it could be that I say, okay, please take this stack of papers and put them into the cabinet. And the idea is that the robot should then, like itself, autonomously be able to come up with a plan that solves the problem. Okay, this is something we can do, and how do we do that in AI? Well, first of all, we need to tell the robot how it can interact with the world. So if I tell a robot to put the papers into the cabinet, it needs to know that it can actually pick up the papers, right? It needs to know that it can open the cabinet. Well, it might know that it can open the cabinet, but it might have no idea about what happens when it opens the cabinet, okay? So we need some kind of action descriptions, and this is the first place where we use some logic in order to describe this to the robot in order to allow this robot to act in the world. It's the same for humans, essentially, right? We cannot act in the world if we have no idea about what the consequence of our actions will. We can plan, we don't have an option, we don't have a possibility of planning our actions. So what we can do with this robot is that we can tell it that, okay, you have certain actions available and they have certain consequences. For instance, if you have an object X, you can pick it up, right? So this is what I have on my slide. The effect of that action will be that I'm holding X, okay? Of course, if you can pick up things, you can probably also drop them down, and then you're no longer holding them. What else can you do? Well, you can open stuff. If you have a container, you can open it, and then it's open, and you can close it, and then it's closed, okay? And then what else do we need in order to solve this problem? Well, I need to be able to move things around. It's not enough to be able to pick up things and open things. I also need to be able to move things. So now I have this action description. So this describes the action of moving object X from Y to Z. And it has some preconditions. So this is what has to hold for the action to be applicable, and this is the effect. What it essentially says is that I can take this stack of papers X, and I can move them from position Y, which is the table, and I can move them into position Z, which is the container. But it requires that the papers are initially at the table, that I'm holding them, and that the cabinet is open. This is what I describe in the preconditions up here. Okay, and when you have this, okay, so when you have the description of your individual actions, then the problem you're trying to solve is to stitch together these actions in a way that achieves what you want to achieve. So I could say to the robot that the goal is to have the papers in the cabinet, and the cabinet has to be closed. And then the robot looks at these actions and tries to stitch together a solution that brings the system to the goal. And how does this work? Well, it's essentially the same as is done with Google Maps and the GPSs in cars. So let's try to look a bit at that. Okay, so I might want to find the shortest route from Herning to Copenhagen, and let's assume that these are not the road segments that exist. These are a bit odd, but assume that. And the problem I want to solve is to get from Herning to Copenhagen. Well, it's a simple problem, right? I just find the shortest path through these different nodes, these different points, okay? Now, the idea is that well, this can be made more general, and we can abstract away from the fact that in this case, the points are positions on a map. They don't have to be. They could be states of an arbitrary system, like the system of a robot that needs to move things around. So for instance, Herning could be representing that the papers are at the table. So now they represent this state where the papers are here. So Aarhus could be representing that the papers are at the table and the cabinet is open. And that would mean that the connection between Herning and Aarhus corresponds to the action of opening the cabinet, because opening the cabinet is an action that takes me from a situation where only the papers are at the table to a situation where the papers are still at the table, but also the cabinet is open, right? And the idea is that you can now search through these kind of structures, so it becomes like finding a route from A to B, but just in this system of states of a system. And it ends up looking something like this. So let's see. Oh, I have to go this way around. So if you look now at the red path, what is it representing? Well, it says first open the cabinet, okay? Then it says pick up the papers, okay? It says move the papers into the cabinet, drop them. So this is, I mean, you have to be really explicit with the robots, right? If you say to a human, put the papers into the cabinet, it will probably also drop them and leave them there, right? But for a robot, that's a separate action. Drop them, close the cabinet, done. And then we're at the goal. So now we're in Copenhagen, right? And this is how it works. So far that seems simple, right? Because if we can describe our actions, if we can just give a goal and it can search like Google on Google Maps, then we should be able to solve any type of problem. Yeah, but it's okay. It's not that simple. So let's look at some of the complications. Right. So recall what the goal was. I stated that the goal was that the papers are in the cabinet and the cabinet is closed. Okay. So why would I say that the cabinet has to be closed? Couldn't I just say, okay, I want the papers in the cabinet and then that's it? Well, okay, let's see what would happen if that was indeed the case. Well, then the robot that tries to solve the problem could get off in Odense, right? Odense is the first state on this red path where the papers are in the cabinet. So it would be opening the cabinet doors, pick up the papers, and do like this, and say, okay, now the papers in the cabinet, right? It didn't drop them or anything, but the papers are in the cabinet. And then you would say, yeah, okay, I said to put the papers into the cabinet, but what I actually meant that you should leave them there and close the cabinet. And this is kind of a cultural norm, and we should teach our robots to understand those cultural norms or what is implicit when we specify a goal. Yeah, but it's actually not that simple, because in this case, of course, if I just say to a robot, put the papers into the cabinet, and the cabinet is closed, this is probably what I wanted to do, put it in, close the cabinet. But then look at another example. So assume that I'm going with my family on a car trip, and we have 2 suitcases, and then my wife asks me to take one of the suitcases, and I go first, and then I open the trunk, I put in the suitcase, I close the trunk, I lock the car, and my wife is just behind me. And then she has to unlock the car again and open the trunk. That would be super annoying. And she would say, why would you do such a thing? You knew that I was just behind you with another suitcase. So the point is, we cannot just generally say that if someone is, if you ask someone to put something into a closed container, what you always imply is that, well, after you leave, the container should be closed again. That's not universally true. So what is it? Well, it actually depends on taking the perspective of the person that gives you the task, right? In certain circumstances, you want the container to be closed, in others not. So the only way I can understand that I shouldn't close the trunk and just leave it open for my wife is, of course, because I'm able to take her perspective. And this brings me back to this point about social intelligence, that this is a problem we try to solve, and it's not yet solved with these kind of techniques. We need something more advanced than what I have so far. But, I mean, what is here is still nice. It's called automated planning, and it works very well, and you can implement it on robots, and it's very robust. But, okay, so maybe only if you have 1 robot, and already if you have 2 robots, it gets complicated. If you have human beings, it gets even more complicated. So, let's try to look at the situation of solving this amazingly simple problem of getting a stack of papers into a cabinet, but in a situation where you are not alone in the world, okay? Because the problem with these Hello Hospital robots was that when there are other human beings involved, things get complicated and things start to fall apart. So, okay, so what I'm going to show you is a video. It's actually an experiment from cognitive psychology. And, well, the goal is actually to get the papers into the cabinet. But the small boy that is standing in the corner actually doesn't know initially that this is what the experiment is about. So let's see what happens in this case.
Oh. Oh.
So this is an example that illustrates that, I mean, it's much more complicated than just getting papers into the cabinet when you're alone. So in this case, the child has to do a lot of things. First of all, the child has to recognize what the goal is to get the papers into the cabinet. This requires that he's able to take the perspective of the adult. And then you can say, okay, but then he just needs to come up with a plan. And I already showed you how to come up with plans. If you have a goal, you just find a sequence of actions that brings you to the goal. Yeah, but that's not even enough in this case, because it's not the child that alone solves the problem afterwards, right? The child goes up and opens the cabinet doors and then leaves it to the adult to finish it and get to the final goal. So the child also has to think about the abilities of the adult and what the adult can be expected to do as a consequence of the actions of the child. So again, there's a lot of perspective taking going on. There's a lot of putting yourself into the shoes of others and trying to take their perspective and reason about what they can do and what they think and what they want. And this is the kind of stuff that I'm very interested in, well, trying to solve as good as I can with artificial intelligence. And to kind of, this is a bit complicated. I mean, already this example, it seems simple maybe, but this is already a bit complicated. So let me try to make a slightly simpler example. So let's assume that I'm throwing a party, and you're all my guests at this party, and there are 3 types of drinks at this party. There's beer, there's red wine, and there's white wine. Okay. Now, to make this party a bit interesting, you don't all know where everything is located at this party. So you just have to remember that there's these 3 drinks. That should be easy. And now I'm going to take them away for a while. And then I'm going to do like this. Whoops. Okay. So the one sitting right in the middle might be a bit challenged, but the rest, it should work out. So if you can see both sides, you're cheating. That's not allowed. The point is now that those who sit in the right part of the room can only see the drink in this side, and those who sit in the left part of the room can only see this drink. And also, I put a drink inside the cabinet. I'm not telling you which one it is. Okay. It could be. I mean, one option is that what I did is to put the whoops. Things are not working as I want today. What happened? Okay, yeah. So, right. So it could be, I'm not telling you if this is actually the truth, but it could be that those of you who are on the left side is seeing red wine, those of you who are on the right side is seeing white wine, and the beer is in the cabinet. And then I can say, oh yeah, but okay, I can describe that as before. I give a logical description of this state of affairs. And later I'm also going to use a slightly simplified picture of this. So I put an L above the drink that is on the left side, and an R above the drink that is on the right side, and the drink in the middle is the one that is in the cabinet, okay? Right, okay, so it seems simple. I just make this logical model of the state of affairs, but now the problem is this. I want to be a good host, okay? I want to make sure that everybody knows where all the drinks are located, so you don't have to run around looking for your drinks. So I should probably tell you, right? I would be a good host by telling you where the different drinks are. Okay? I could consider that. How would that affect my model of the world if this is my model? It's either this logical description or the picture. Well, it wouldn't. I could, for instance, say, oh, there's beer in the cabinet, by the way. Okay? But if you look at the model, it says that there's beer in the cabinet. And now I'm telling you that, well, and there's still beer in the cabinet. Nothing changes, right? So why would I ever choose to do an action like telling you that there's beer in the cabinet? Because it doesn't change my model, right? I only want to execute actions that bring me towards some goal, but this action doesn't make any change at all. So I might as well not say it. Or it could also be that I said, okay, there's beer in the cabinet, 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 and I keep saying it because no matter what, I don't see a change, right? Either I keep quiet or I repeat it and I can not see a change. So what is the problem here? The problem is that my model is a model of the physical world of drinks and locations. If I tell you that the beer is in the cabinet, nothing physical changes in this room, but something changes inside the head of all of you, right? Your mental state changes, right? Because your mental state before you didn't know, right? You cannot see what is on the other side. So you don't know. I mean, if you're sitting over here, you don't know what they're seeing. So you also don't know what is in here, right? But if I'm telling you that there's beer in the cabinet, then you know. And this is what we want to have inside these models in order to be able to deal with these scenarios. The point is simply that also these robots and computers and whatever that need to take the perspective of others, they need to be able to represent the mental states of others and reason about those mental states. And well, that's not completely trivial. So it actually brings me back to that. Now I'm going all the way back in history, because it's actually part of a very general thing that when we in AI want to create systems that can solve problems, then we think about, well, we often think about how are humans solving these problems. So we want to simulate certain aspects of human cognition. So it could be our ability to plan or think logically or something. Okay, so it means that we want to have this into a computer. We want to be able to make a computer that can do these things. The only way we can achieve that is if we can build a mathematical model of the phenomenon we want the computer to be able to handle. So if the computer should be able to plan, we need to build a mathematical model of planning. And if it should be able to think about others and the mental states of other individuals, well, we need a mathematical model of that. And of course, this is part of a much more general thing that we also use mathematics to try to model the weather and the stock market, because we use that to predict how the weather and the stock markets develop. So I like very much this quote by Galilei that the great book of nature is written in the language of mathematics. So all like phenomena and natures that we want to put into a computer, we first have to build a mathematical model. And this has a long history, going back to numbers and counting 30,000 years before Christ. And then I'm talking about logical models. So that actually builds on Aristotle, and that's already 300 years before Christ. And then we got differential equations with Newton in the 1600s and used to model physical movements. What you can see in this timeline is that as we progress in time, we are modeling more and more complex phenomena in nature. And then at some point around the 1950s and 1960s, we start to get AI going. So first we have something logic-based AI that points back to Aristotle. Then soon afterwards, machine learning gets started with, and that is actually built on differential equations. So it points back to Newton. And then much later, well, not okay. So in the long history, not that much later, but the kind of models I'm using in order to represent other individuals is called dynamic epistemic logic, and that only have existed since 1998. But anyway, so we are modeling more and more complex phenomena or more and more complex aspects of nature, and well, there's of course always this speculation whether eventually we'll be able to model all aspects of human reasoning. So will we be able to make AI that can somehow do anything that a human can do? I don't know. And also, this is not what I attempt to do, I should say. So no matter whether you would like or dislike that idea, this is not what social aspects of AI, in my viewpoint, is about. This is not where I want to get to. But I just want to make sure that at least they are socially intelligent enough that they can drive around in hospitals without having to be given up. So I'm now becoming a bit more general because I also wanted to make a reference back to the start of my career, because there is like a line through the stuff I did. So one important thing that happened on this timeline that I didn't put is that around the 1920s, we began to see logical models of mathematics. So mathematics had a foundational crisis around 1900. And people started being very nervous about mathematics and thought, okay, we need to get mathematics on safe ground. And then you started to build logical models that were very precise, and that should hopefully we should hopefully be able to use this to rebuild mathematics in a sound way. At first, it sounds as having absolutely nothing to do with my general talk, right? But actually it does. Actually it does. Because what does it mean to build a logical model of mathematics? I talked about logical models. I talked about models of paper stacks and cabinets that can be open or closed. These are also logical models of an external world, right? What is special about creating a logical model of mathematics is that logic is part of mathematics. Right? So if you manage to build a model of all of mathematics within logic, then since logic actually is inside mathematics, then inside mathematics you have a model that models everything, including itself. And this is actually the kind of situation we're also facing when we want to start to build models where we can take the perspective of others. At first it sounds crazy, but actually it's not, right? Because those of you who are sitting on the left, And you look at these strings, and you wonder what the other guys are seeing, right? So you try to create mental models of the people on the right. But they, of course, also try to create mental models of your mental models, right? So inside your head, you have a mental model of those guys, but inside their mental model, they have a model of you. So eventually you have this situation that it's not only about modeling the external world, but you're ending up modeling a part of the world in which you're yourself included. And this is exactly the situation we have with these logical models inside mathematics. And just to illustrate it, so, I mean, it can easily get very technical, so I thought about trying to make an illustration of it that somehow points to the problem and it's not technical. So you cannot see it, but I have a webcam up here that can point in different directions. And we can think of what the webcam is showing as a kind of model of a part of reality. So right now, it's a model of the part of reality where you guys are sitting in the audience. Okay? And I can do like this. I can invert colors. So now I have an inverted model of reality. And what is interesting is this situation where you say, oh yeah, but it could be that the model itself is part of the world that you want to model. Okay? And this happens when I point the camera to the screen. Then I get exactly this. And immediately you can see that I get this like infinite fish trap, right? Because if inside the model there's a model of the entire thing, then inside that there must be again a model, etc., right? So, and let's look at something interesting here. So now I tilt it a bit. And let's try to go a bit closer. Okay. Okay. Okay, it has to stabilize. So give it a second. But actually, so what ends up happening is that you have a point in the middle that keeps flickering. So why does that happen? Well, the thing is, you have these nested models inside one another. And there will be one point at the bottom of this infinite fish trap that is trying to represent itself. There's one single, so actually it's a contraction. There will be a fixed point for the mathematicians in the audience. So there will be a fixed point. Right, but the representation is negated. You negate the color values, right? So there will be one point that cannot decide on which value it should have because it represents itself, but it negates its own color. So it will forever keep flickering. And that actually, well, it sounds maybe a bit odd, but that is actually very closely related to some of the fundamental problems that were discovered in mathematics. Because the point is here that we can say it's not possible to have all of the following three things. A system that can completely represent itself, a system that has fixed points, and a system that can negate things or invert colors or negate truth values or whatever. And actually, these are the main ingredients in order to prove Gödel's incompleteness theorem that the mathematicians will know about. But this is one of the biggest mathematical results of the 20th century that says that essentially, well, in a popular explanation of it, it says that there are true mathematical theorems that cannot be proved. So there will be some complications and limitations as soon as you get into a situation where you say, okay, I want to build a model, but the model should be part of the reality that it models. Okay? Okay. So yeah. And it's quite funny, right? Okay, so back to the main story, and I should maybe also improve the colors a bit again. So why am I saying all this? I'm saying because, well, first of all, just to illustrate that, okay, funny things happen when the model is part of the world that it tries to model. But also just because it actually points back to where I started my career, because I started being very occupied with the foundations of mathematics and Gödel's incompleteness theorem and self-reference and all this kind of stuff. And even though it might not be immediately obvious, there is actually a direct line to this state of thinking about social aspects of AI. Okay? Okay. Now, so what is the solution? Okay, I promised somehow, I said that okay, it's going to be a bit complicated, but let's see how can we actually solve this problem of trying to represent the mental states of others. So I'm back to my party now. You are still my guests. And now I want to do better than before. I want to make sure that I have a model that correctly represents the mental states of my guests, so I know what to say and when to say and what would happen when I say stuff, okay? Okay, so in that case, it's not enough to just represent, it's not enough to just represent the world like this, even though it could be that this is actually the true state of affairs. But because first of all, I have to realize that the ones sitting to the left, they're actually not seeing what is on the right. So they don't know what is in the cabinet either. So they cannot distinguish these two states of affairs. And now I have to be a bit careful and let you know that before, when I had points and I had these connections between them, it represented actions that took me from one place to another. Now what these connections represent is that those are states of affairs that cannot be distinguished by those people whose name is on the connection. So what you see now is that the people on the left cannot distinguish between whether the white wine is here and the beer is in the cabinet or vice versa, right? And hopefully it's true. Okay, but now the point is that I'm not quite done yet, right? Because okay, so the ones on the left, you think that it could actually be that the ones on the right is seeing beer. But then you can also take the perspective of those guys, because if they're seeing beer, what do they know about the world and what are they not sure about? Well, they would not be sure about whether, in fact, this is the true world, right? Because if the ones on the right is seeing beer, then it could be that you're seeing red wine, but it also could be that you're seeing white wine, okay? And the point is I can continue this. So because you can take their perspective, they can take your perspective, and then you can have these perspectives looping back and forth. So the model develops and develops and develops and develops and develops and develops, and you end up, well, you never end, right? Because you can continue doing this. And I don't know if this looks familiar. It should look a bit familiar, right? Because it actually should remind you of this picture with the webcam that was showing the picture of the screen. Because again, we get this kind of infinite fish trap. But luckily, we are here in a slightly simpler situation, because actually these two guys are identical, and I can just identify them, boops, and then the model is like this. So now it's cyclic, but it works, okay? So this is a full description of the state that we're in. You might not believe me yet, but it is. So let's see. Okay, so now I'm the host at a party, and this is instead my model. And now I can consider what to do, okay? Okay, so I could consider giving you a piece of information. I mean, I could tell you where everything is located, but that's actually not necessary. I could just say, okay, the beer is in the cabinet. And now actually something will change in this model, because if you look at this model, there are certain possible states in which the beer is not in the cabinet. So in this one, in this one, in this one, and in this one. So in neither of those, the beer is in the cabinet, okay? And if I tell you, then everybody knows that the beer is in the cabinet. So these possibilities simply disappear. So if I tell you that the beer is in the cabinet, what we will have left is only these two possibilities. And in both of them, you know exactly where the different things are, because now you're no longer uncertain about anything. You don't have any connections to anything else. So now if I'm a robot or a human or whatever, I actually, before it didn't have any effect for me to let you know that the beer is in the cabinet, but now it has an effect. It has the right effect. But interesting, I can also do something slightly more sophisticated. I can if we go back to the beginning, I can also say, none of you know where the beer is. Okay? None of you know where the beer is. And then you nod and say, yeah, it's true, none of us know. No, but now you know, right? The point is that just by saying that, you end up knowing where the beer is. Why? Because now you know that none of you knew. So what is going on here? Well, exactly. So let me see. So if I say that none of you know where the beer is, I say it's impossible that we are in one of these situations where some of you know where the beer is. But if we start up here, right, then the guys on the left are only confused about whether we are in this one or in that one. But in both of those, the beer is in the same location. So it would not be true that none of you know where the beer is. And the same is the case for this connection. So actually, if I say none of you know where the beer is, we get exactly the same update of the model, and you will all know where the beer is as a consequence of that. So it's not completely trivial, as you can see, but we have now the models that can do this. And of course, this is only the beginning, because I mean, there's a lot of things that has to do with social intelligence and taking the perspective of others that is not already, I mean, that is not necessarily captured by these models, but it's a step in that direction. So I don't have so much time left. So first, this is a service. This is a service message for the hardcore mathematicians in the audience. In order for, I mean, okay. So now I gave an example that involves alcoholic drinks. So I'm pretty certain that at this point everybody is longing for the following reception. And then I shouldn't start getting super technical at this point. But I just wanted, I mean, for the few of you who have those interests, say that, well, kind of this ghost of problems about models that can represent themselves is kind of still with us in this framework, because it turns out that if we want to do planning, so planning, again, remember, it's you want to achieve your goals. But now planning is not planning for me as an individual, but it's planning where I take everybody into account and I reason about your mental states, etc. Okay, so if we do planning based on those structures, it's undecidable. It means that, well, in general, we cannot be guaranteed to find a solution. And then what I've been doing in much of my research is then to say, okay, but this is just when we have full generality, we can cut down and make it simpler or restrict it so that it becomes decidable. And in a way, you might think, okay, even if you know about theoretical computer science, you might think, okay, but why is there anything related to undecidability and complexity and theoretical computer science in AI? Because inside the human brain, we are not. I mean, when we think about other people, it's not like that we can reason about exactly the kind of structures we have and whether it's undecidable or decidable. But the thing is that in many cases, we want to give guarantees, right? So we build a robotic system, or we build a system of interacting robots, and we want to give guarantees that under such and such circumstances, these robots cannot fail. Right? If we want to do that, of course, we need to have the models we use should be as general as possible, and we need to come up with proofs that it either works or it doesn't work. So actually, these kind of problems will be essential in those types of situations where you want to be able to give guarantees. Okay, so what else did I do? Where did I go with this? Well, well, a bit more than a year, we have been working on this Pepper robot. So our Pepper robot is called R2 DTU, and my beautiful assistant Lasse, where are you? I saw, yeah, my robot programmer. So this is something we did together, or it means that he did most of it. Trying to implement these ideas and try to make the robot solve these kind of problems, where it has to be able to take the perspective of others, right? And this is now where actually this combination of many areas of AI come into play. Because The robot needs to do a lot of things. Okay, so it needs to do planning, it needs to take the perspective of others. I can do this with logic, no problem. But a robot also needs to perceive the world. It might be that it knows that when it opens the cabinet, it's open, but it also needs to be able to see the difference between an open and a closed cabinet. It also might be that it actually doesn't know what happens when you put stuff into a cabinet. For instance, it might be you might be in a crazy Harry Potter-like fantasy world. You put stuff inside, and then when you close and you open again, it's suddenly gone or whatever. I mean, you might not know, and you have to learn, so you need machine learning for that. So this is also something we look at. Actually, learning actions is something I look at together with Nina Gerasimchuk, who's here, and Andres, I think, is here. So our joint PhD student, yeah, cool. No, so the robot needs to do a lot of stuff. It needs to do perception and learning, so there's some machine learning involved. But it also needs to reason about its possible plans and the mental states of others, and this is where the logic-based AI is coming into play, and then it's on a robot. And one thing that is really super cool at being at DTU, and now even as a professor, is that it has been acknowledged that we have world-class sections within both the machine learning paradigm and the logic-based AI paradigm of AI. And we also have a great group working on robotics. So my long-term ambition in research is that all of these things come together, because in a sense, this is what we need in AI. I think of this as the holy grail of artificial intelligence, to combine the paradigms. Because logic and explicit linguistic reasoning is not enough. It's not only what we humans do, but perception and learning from observations is also not the only thing that we humans do. We do both. And the combination is crucial, right? Because the fact that we humans do explicit linguistic reasoning, we use words and sentences and reasoning and logic when we come up with decisions, that's quite crucial. Because it means that since we used linguistic reasoning to get to our decisions, we can also explain those decisions to other people. And this is a fundamental part of the trust between humans. We're not just doing stuff. And if somebody asks us, why did you do it? We have no idea. We have an idea because we actually used, well, not necessarily logic, but you used explicit reasoning to actually think about what to do. But again, it has to be combined with the other paradigms in AI. And this is very ambitious. I mean, as I said, it's the Holy Grail. So I just want to be part of the search team for that Holy Grail. And I don't know how long it will take to get there. But I mean, it might take long, but also I'm only halfway through my career, so there's still hope. And I think DTU is a really cool place because we have great environments in robotics and in logic-based AI and in machine learning. So, final words. I want to thank some people. I already mentioned a few. So, one of my PhDs, one of my colleagues, Nina Lasser, my robot programmer. And first of all, I just wanted to thank all my all my current and previous bachelor, master, and PhD students, and all my research colleagues, and everybody who has somehow been part of this long travel for me. And then I want in particular to thank a few people that have been the supervisors of me during the years. So first there's Helge Elbrandt, who's also somewhere in the audience, who was the master thesis supervisor. He was the co-supervisor of my PhD. And then the principal supervisor on my PhD was Jørgen Fischer-Nielsen. And then I also want to thank Paul Fischer, because many years ago, we together had this vision of creating a strong section in logic and algorithms and its applications to artificial intelligence. And we actually managed to realize that vision together. So I'm very grateful for that. I'm very grateful for all three people and the influence you had on me. And then, of course, very importantly, my family who is here on the front row. And it's not exactly because they wrote my scientific papers. It's not exactly even that they always kept quiet when I tried to finish my scientific papers. But even then, I mean, they created the space, and they created sort of, they they created the opportunities and the space for me to actually allow myself to pursue this academic career that brought me where I am today. So that will be my final words. Thank you.
Thank you, Thomas. Do we have sound? Do we have sound? Some sound. Thanks it's really great to be part of your party and having one's mental state modeled a little bit. Yeah. I think we should allow ourselves and everyone to have one or two questions for Thomas. So by all means.
Nobody dares. Well, I'm already predicting your mental state, so.
we had this additional mic somewhere.
Yeah, we might, but. Yeah, you can shout.
I can shout.
But it's a bit with.
First, and then, yeah.
Okay.
I don't know.
So your timeline.
Yeah.
The timeline that you showed of mathematical modeling is somehow culminating in singularity, right? So you're kind of going through history, drawing one line that is kind of a optimal goal of mathematical modeling. Do you see it as, is it just an example? Do you think mathematical modeling is going strictly that direction? This is the most important direction?
No. I don't know why I did that. No, I think. Well, I think.
Well, I agree with you. To some extent.
No. Okay, so the point is.
Controversial point.
The point is, if you look at the history of mathematics, you're looking at the history of capturing parts of nature in precise mathematical terms, right? And that starts, well, obviously with simple stuff. And the simple stuff is like numbers, and then it gets more and more complicated. And it's only recently that we even started to dare thinking about trying to model something that has to do with what happens in here, right? And I don't know where it's going to end, right? So it's not necessarily the goal. The question mark here means that it's just it will be interesting to see, right? It might also be impossible. There might be certain limitations. I showed you several limitations. There were incompleteness and in undecidability. There might also be some limitations we don't know. Singularity, that could be scary. So not necessarily no. Is that what I want or aim for at all? It's really just for this project, it's really just that currently most AI systems are simply utterly social analphabets. They can do nothing, and then that is too little, right? If we even for these hospital robots that just need to put things from A to B. I don't know if I'm answering, but yeah.
First of all, congratulations on your professorship, Thomas.
Thank you.
Going back actually to the very first example you came forward, these delivery robots for the hospital.
Yeah.
In that context, I think that one of the reasons they've been parked in the garage, as you mentioned, is the inability to live in the same space with human.
Yeah.
But that maybe was also the inability of the human to collaborate in the same space with robots.
Good. Yeah.
So, because in your approach, I think in this logic-based AI approach, you say you develop social intelligence, I think under the assumption of as human behaving as rational beings. But in that context, maybe the mobbing comes from the human acting unrational because he wants to see what happens if I step in front of the robot.
Yes.
And how do we build that type of intelligence? How do we build that type of interaction?
Yeah. True. Yes. Yeah. So it means that it's just even more complicated than that, right? Because most of what I tried to do was to build the ideal model where also you can assume that everybody else is perfectly rational, right? But so that is something you then have to add that to the model, right? But it's still goal recognition in a way, right? Because okay, so why are you doing this in front of me, right? Are you trying to show that I should stop, or are you trying to tease me, or are you checking whether I can deal with this, or I'm just going to crash if you do this in front of my eyes, right? And that's still intention recognition. And then it might be a bit crazy to think about robots that think about humans that try to trick them into being put in the garage or something. But I think that the issue is that first of all we need to have the models in which it's even possible to represent the mental states of others, right? So that's the first step. And then after that, you can say, okay, yeah, right. But then we have to say that, okay, it might be that what actually goes on in the other individuals is a bit more complicated. So it's a bit like in game theory, where you start out modeling perfect rational players, and then after that you say, okay, but what about bounded rationality, and what if people make strange choices, and that comes afterwards. But it's very important, of course, yeah, because robots might eventually make false assumptions about humans. So for instance, in a rescue team that composed of robots and human beings, this might be a real issue, right? That the robot is this perfect, rational individual that says, yeah, but you ought to know what to do in this case. And the human is just, I don't know what to do. And the robot doesn't say anything because logically, I mean, if you do this kind of sequence of logical deduction, you would know. So you ought to know. Yeah.
So may I add, Thomas, would you like to estimate when will we have the next news piece telling that they are back in business, these type of robots?
Right. That's a very, I mean, okay, so there are hospital robots in many places in the world already, right? But you have to, so it's a question of that two things you can do. I mean, either you can only have robots in designated spaces where these problems don't appear, or you have to come up with a solution. And you can, if it's just a question of solving specific problems, for instance, navigating around human beings, that is not so difficult. But if we talk about the general problem of saying that you should have the general ability of taking the perspective of the people around you, that is more complicated. I don't know. I think we will have news like this all the time from now on. We will have news like this and news like this, and sometimes it works, sometimes it doesn't, sometimes, yeah. And this is what it is in AI, because as I said in the beginning, it's not easy actually to understand what AI can do and what it can't do, and what are the easy and difficult problems for AI. It's difficult for everybody. So we just also have, sometimes you go out and try it, and then you realize that, okay, was a bit more complicated than expected. And in other areas, suddenly you have a breakthrough, and you say, okay, I didn't expect this to happen that soon. Yeah.
Thank you. Last question. Something really important. Yes, please. Can we get the mic?
Something really important? Is that what you said? The last question has to be really important.
That's some kind of pressure. I don't know if it's important. You mentioned that the robots can make false assumptions about human behavior, but so can humans.
Yeah,
and
of
in
course.
those cases,
we do that all the
if
time.
you make a decision based on a false assumption, it might have been better to ask.
Yeah.
So I think your perspective is to build something which is totally autonomous. But how about communication between the units? If instead of you telling us that the beer's in the cabinet, we could have asked the other half, what do you see? That would have given the same result.
Yeah, of course. And that would be your perspective, right? Because if you build that model, it could be so this is a very good example, right? So it could be that you who are on the left, you're sitting comfortable in a soft couch, and then, okay, now I have to go back. I shouldn't have blown it, and I did that too early. And then you desperately want to have a beer, and then the guys on the right, they're all standing up, so they could get beer, right? And then you could say, so now you could say, okay, please, could you give us a beer, right? But would you only say that? Well, no, because you on the left taking the perspective of the right, of the people on the right, you know that that they might not know where the beer is. But if you can give a piece of information that will let them know. You can say, so the people on the left can say, oh, could you please get us a beer? From where we're sitting, we can only see red wine. And that's enough information also for you to know that the beer is in the cabinet. Yeah, so it also works in that. That was not your question, but that was the first step, right? So you can have false assumptions. Yes, of course. And it means that in some cases, you might need to be more informative than minimally according to an assumption of everybody being perfectly rational. And we all, as humans, we also do this, right? Sometimes we just to be safe. I mean, just to be safe, I could say, there's white wine here, red wine here, there's beer in the cabinet. It doesn't cost me a lot to say that. And then I would be on the safe side. And I can repeat it a couple of times during the party because maybe some of you didn't hear or you don't remember. But this can also be integrated in the models. We need some models that are a bit more complicated than this, where we either have probabilities or plausibilities. So we can say that certain state of affairs are more plausible than others. So I could say, for instance, yeah, I know that maybe you know, maybe you don't know whether there's beer in the cabinet. But I can kind of assess how likely or probable or plausible these two scenarios are. And based on that, I can decide, is it worth my energy to tell you something that you might already know? It also depends on how important it is, right? Because sometimes, even though you expect everybody to know, okay, there's a fire in the building, everybody gets out, and you look at the fire, but you say it nevertheless, because, I mean, even if everybody sees it, just to be on the safe side. So all of that can be integrated as well. Of course, it gets very complicated, but it's not out of the question to have that as part of the model. Because again, we're modeling bigger and bigger parts of nature, and every time somebody says, yeah, but how about this? How about that? It's just, well, that's a new challenge. We have to create the mathematical models that can do it. Right.
Thanks. I think we should congratulate Thomas.
Thank you. Thanks a lot.
Tak.
Nå, ja.
Ja.